Hello everyone, welcome to my group theory lecture. In this lecture, we study basic number theory. Number theory plays an important role in studying group theory. We begin with Euclid's algorithm. So here's the theorem. If m and n are integers with this condition here, then there exist two integers q and r with r greater than or equal to 0, less than m, such that n equals qm plus r. So basically what this Euclid's algorithm is talking about is integer division. So when you with the given two integers, right, m and n, with this given condition, right, we can divide the integer n by m, and in that case, there are two integers q and r, which we call quotient, and the remainder r. So this is basically what formal description of the division algorithm that we are familiar with. This Euclid's algorithm, they hints us how we can actually define the notion that one integer divides another integer. Okay, using the operation multiplication alone. Okay, so here comes the definition, right? So the what is that? In the previous theorem, right? Uh, the 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 integer m divides n means that in the case the remainder it has to be 0, right? So we have the following the definition naturally. So given m a positive integer, okay, and n an integer, we say m divides n, and we write this notation here, right? Okay, that's notation for m divides n if n is written as c times m for some, I gotta fix this, for some c, another integer c, okay? Right, so that's clear from the previous theorem. So here are some examples, right? So 2 divides 14. Why? Because 14 is, can be written as 2 times 7. Negative 7 divides 14 because, the 14 can be written as negative 7 times negative 2. And likewise, 4 divides negative 16 because negative 16 can be written as 4 times negative 4. Okay, right. So if m divides n, we call m a divisor or a factor of n. And also in that case, I'm sorry, there has to be a space between them and a multiple of m. So, in that case, m is called a divisor of n, or, n is called a multiple, okay, an integer multiple of, the m. If m does not divide n, we write this notation here, okay. For example, 3 does not divide 5, okay. So 5 cannot be written as an integer multiple of, 3. So here are a bunch of the properties, okay, with the integer division. So these are the using just use the definition of integer division, uh, without much difficulty, one can prove these properties. Okay, in fact, these are the proof of this lemma is left for the readers as an exercise. But you know, so let me just skim through these statements quickly. So one always divides any integer, okay, any integer n, and if m is not equal to 0, then m always divides the number 0. If m divides n and n divides q, then m must divide q. Next property is if m divides n and m divides q, then m divides mu n plus nu q for all integers mu and q. So the expression here, mu n plus nu q, this is often called a linear combination of the n and q. Okay, so in other words, if m divides n and m divides q, then m divides any integer, so any linear combination of n and q. Next one, if m divides 1, then m must be plus or minus 1. And last property, if m divides n and n divides m, then m has to be same as plus or minus n. Okay, so next thing we want to talk about is the greatest common divisor. So here's the definition. Given a and b, not both equal to 0, okay? Of course, we always talk about integers here, right? Their greatest common divisor, in short, we call it GCD. C, so we are calling it C. I gotta fix this also. There has to be, it's not CIS, okay? There has to be a space. So we are calling the greatest common divisor of A and B, C, is defined by the following properties. Okay, so these are the axioms. Okay, for the C to be the greatest common divisor of A and B. First, the C has to be a positive integer. C must divide A and also B. In other words, C is a common divisor of A and B. If D divides A and D divides B, in other words, if D is another common divisor of A and B, then D also must divide C, right? So these three conditions are the axioms for the greatest common divisor. So if C is the GCD of A and B, if we write it by this notation, in different like textbooks, they also use like C equals GCD of AB, but in my case, I'm going to use this just parenthesis notation for the GCD of A and B. Okay, so here's an important theorem. If A and B are not both equal to 0, their GCD exists uniquely. Moreover, there exist m and n, two integers m and n, such that C equals MA plus MB. In other words, in the case, we have, so this is an equation. So this equation has a solution m and n. Okay, so the integer solutions m and n. Okay, so let us talk about the finding GCD. Oh, actually, I might show you actually an example before we go any further. All right. So let me go to my notepad. So let us consider. Okay, let us consider the GCD of 24 and 9. Okay, these are small numbers. Okay, so how do we find GCD? Where the crude way we can find what is that greatest common divisor of 24 and 9. So the first you write out the divisors of 24. So divisors of 24, that will be 1, 2, 3, 4 is also a divisor, right? And 6, 4 times 6 is 24, and 3 times 8 is 24, so 8 is also a divisor, okay? And then 2 times 12 is 24, and then lastly 24. I don't think I missed anyone, right? And then, so divisors of 9, that's even easier, right? 1, 3, we have 1, 3, and 9. Okay, so here, now that we selected, what is that? Common divisors. Okay, well, in this case, actually, we have only one common divisor, which is 3. So that is going to be our, greatest common divisor. Okay, so that's gonna be 3. Okay, so that's easy. All right. Anyway, when you do have like what two small numbers, you can always find the greatest common divisor in this way. Like if you have more common divisors, by the definition, the largest one is going to be the greatest common divisor. But the difficulty, enormous difficulty arises when you have like, when you are dealing with two big numbers and try to find, the greatest common divisor, the GCD of those two numbers. So what do we do? Well, later, soon, we are going to devise a way to calculate it, uh, I wouldn't say easily, but in an easier manner. So basically, like the if I give you the heads up, the we can actually keep on reducing the numbers, okay? So, the numbers that we are actually dividing. So, those smaller. So if we get down like a smaller pair of numbers, right, which gives us, the same GCD uh, of the original pair, then of course, we are playing with a smaller pair, a pair of smaller numbers, so it is easier for us to find, uh, the GCD. Okay, so that's the idea. Anyway, in this case, what's interesting to know is that, this GCD, okay, this GCD3 can be written as, written in terms of these two numbers, 24 and 9, okay? In fact, this can be written as 3 times 9 plus 1 times negative 24, okay? So that's one way you can write. And also this can be written as negative 5 times 9 plus 2 times 24. Okay? So in other words, what is that? We just saw two solutions, right, of this equation. The m times 9 plus n times 24. Okay? So, for a long time, the solving this type of equation, okay, this type of equation has been a great interest in number theory, okay. This type of equation is called a Diophantine equation. Named after uh, a Greek mathematician, Diophantus, who uh, who studied this type of, the equations first. Okay, right. So this is very important. And also, as you can see, we found, the two solutions, right? So M and N. So we found two solutions. One is like M equals negative 5, N equals 2. Uh, the other one is M equals uh, 3 and N equals oh, actually, you know what? I want to write this as yeah, because I'm sure trying to write out, the solution of this equation. So actually, I should written it as negative 1 times 24. That's looking better. Okay, so m equals negative 1. All right. So as you can see, the Diophantine equation, the solution of a Diophantine equation are not unique. Okay, are not unique. So in general, right, in general, we have this theorem. So again, if a and b are integers that are not both zero, their GCD exists uh, uniquely. Okay, GCD exists uniquely. Moreover, oh, I'm sorry, I found another typo. So, I gotta fix this also. There exist two integers, m and n, such that C equals MA plus MB. So, the solution to, in other words, we have integer solutions that of this Diophantine equation. Okay, so now next thing is, I mean, the practically important thing. So how do we find the GCD? Like I said before, when you have a pair of two small numbers, it is easy to, find their GCD. So it's crude, but you just write out, uh, the divisor, all the divisors of each number, and then mark the common divisors, and then pick the largest one, right? So that would be it. However, that's just not a feasible way to do if you uh, have a pair of two large numbers. It's going to be a daunting task if you try to find the GCD by such the crude method, right? So we wanna come up with we wanna devise a smarter way to do this. Okay, so the we wanna find this. So the GCD of A and B with in this case assumption is A is greater than B, right? So by Euclid's algorithm, we have in this case A equals BQ plus R, okay? Right, BQ plus R, where, R is greater than or equal to 0, less than B, okay? Right. So maybe I gotta get to, right, I'm gonna go to my notepad. So here I wanna talk about finding the GCD. Okay, so like I just mentioned, so we have this, okay? So A equals BQ plus R, BQ plus R with R greater than or equal to 0 and less than B. Okay, so let us let C equals the greatest common divisor of A and B. Then, C divisor, what it means is that C is a common divisor of A and B. So C divides A and also C divides B. So here, C divides A and C divides B. Then, by one of the properties in the lemma, right, previous lemma, A must divide C also, okay? A must divide C as well, okay? Right. Because, the reason for that So, R can be written as, in this case, A plus B times, let me write it this way, negative Q. Okay, negative Q. All right. The reason I'm writing this way is, again, the addition is addition and multiplication. So, addition is an operation. Minus is not a binary operation. Okay, that's actually the inverse element. Okay, so I wanna write it in terms of its operation. Anyway, what do you see? So R is actually a linear combination of A and B, right? A linear combination. So if you remember one of those, the properties in the first lemma we saw, right? So here C divides A and also C divides B. So C must divide, right, any linear combination of A and B. R is one of those. So what this means is R must divide. So then R must divide B, right? So this means is that what this means is that oh no, I'm sorry, not R, but the C, right? C must divide. Since C divides A and C divides B, C must divide R. So C divides, all right, C divides R. Okay, C divides R. And C divides B, C divides R. So this means that, okay, C is a common divisor. Okay, so C is a common divisor of B and R. Okay, B and R. Now, I want to claim that actually this C is the greatest common divisor of B and R also. So to show that if D divides B and D divides C, so in other words, D is another common divisor of, I'm sorry, not C, R. So if D is another common divisor of B and R, then the D must divide A because A is a linear combination of B and R, right? So by the same property I quoted earlier, D must divide A. So in other words, D is a common divisor of A and B, okay? D is a common divisor of A and B, but we already know that C is the greatest common divisor of A and B, right? So that means D must divide C. Okay, D must divide C, right? Okay, so what does it say? This implies, in this case, so, we know that C is a common divisor of B and R, but then if you bring like another common divisor of B and R, then, D divides, D must divide C, so C is also the greatest common divisor of B and R. So what does it say? We actually get down to, the starting out with, right? So C is the greatest common divisor of A and B. But then we can actually come up with a pair of smaller numbers, two smaller numbers, which gives rise to the same greatest common divisor. Obviously, the finding the GCD of the two smaller integers is going to be easier than the previous one. The thing is, we can continue this process. Okay, we can continue to because uh, these numbers may still be like not large for us to uh, be able to find the GCD. So, but we can continue this process. Okay, we can continue this process as you can see from an example. So basically, this is what I just explained. All right. Yes. Okay. All right. So here's an example. Okay. Here's an example. So let's work it out. Let me get to my notepad again. So example. So I want to find in this case. So we want to find it. Okay. We want to find the GCD of 128. Okay. 128. All right. So here we go. First thing is using Euclid algorithm. Okay, so I'm gonna use a different color here. Okay, next to it. So if you divide 100 by 28, so the quotient will be 3, and the remainder equals 16. Okay, so here 28 is going to be where my B, right? Okay, and 16 equals R. So by the previous discussion, we know that, okay, this equals the GCD of 28 and 16. All right. So already like it has gotten a lot smaller, right? Okay. But we don't have to stop here. We can continue the same process. So next, what we do is we divide 28. We divide 28 by 16. Okay, then the quotient is 1. The remainder is going to be 12. Again, so in that case, the GCD of 28 and 16 is the same as the GCD of 16 and 12. Okay, we can continue on. So let's go further. Now this time we're going to divide the 16 by 12. Okay, that's already easy. I meant to use different color. Keep forgetting. So 16 equals 12 times 1 plus 4. So that equals the GCD of 12 and 4, but 12 is a multiple of 4, okay? So in fact, 4 times 3, so the GCD is simply 3. So we found it, okay? Yeah, we found it. That equals 3. No, I'm sorry. What am I talking about? You know, the great 4 divides 12, 4 divided by 12. Okay, I'm sorry. Uh, so it's actually 4, right? It is 4. Yes, 4 is a divisor of 12, right? 4 is a divisor of 12. So yeah, the GCD equals 4. Okay, good. Excellent. So now, next thing we want to do is, okay, so we want to find M and N, okay, satisfying the following equation. So so the Diophantine equation I was talking about earlier, right? So M times 100 plus N times 28. Okay, right. So let's talk about this. Okay, in fact, this can be done by, in the previous example, right? Okay, so in fact, we can use the previous example to find the solutions. Okay, uh, or at least the one solution of the Diophantine equation. This Diophantine equation by working backward of the process we did in the previous example. Okay, so here is how we can do. Right. So let's just start out with so we are gonna focus on these the things on the right side, right, in blue. Okay. So we started out with the very last one, and then we are actually going backward. So start out with it 4. Okay. So 4 equals if you solve this for the remainder 4, you have 16 plus, again, I don't want to use like a minus sign. So 16 plus negative 1 times 12, right? That's what we have. Okay, now that's 16 plus negative 1. Now, the previous equation, our previous expression, okay? So if you solve it for 12, we get 28 plus 16 times negative 1. So replace 12 by that, okay? So 12 can be written as 28 plus negative 1 times 16. All right? This equals uh, negative 1 times 28 and plus that's gonna be 2 times 16. Okay, so by now you will see where we are heading at. Okay, right. So I'm sure you've got some good idea by now. So negative 1 times 28 plus 2 times instead of 16. So 16 can be written as 100 plus right 100 plus 28 times negative 3. Okay. All right. So that can be written as so 2 times 100, 2 times 100 plus negative 7 times 28. So voila, we are done. You know that we found m and n. So in this case, what is that? M equals 2, right? M equals 2. So we found a solution. M equals 2 and n equals negative 7. So we found a solution of this Diophantine equation. Okay, cool. I think this is a good point to stop. So I will continue our discussion in my following lecture. Thank you.